Hello everyone, we are Group 7 and we are explaining the paper that is Reusable Components for Online Reputation Systems. Reputation systems have been extensively studied in various fields and applications. However, a major issue is that most existing reputation systems are developed from scratch without taking into account established concepts and achievements from other sources. As a result, valuable models and effective approaches often go unnoticed. In this research, the objective is to promote the reuse of trust and reputation system by presenting a hierarchical taxonomy of computation engines. This taxonomy serves as a natural framework for designing new reputation systems, incorporating existing knowledge and concepts. Additionally, to aid the design process, the author has provided a component repository that offers design knowledge at both the conceptual and implementation levels. To assess the effectiveness of this approach, they conducted a descriptive analysis based on the scenarios, which clearly demonstrates its practical utility. By comparing the identified components with the trust properties discussed in this paper, they also highlighted the extent to which common models cover different trust properties and identify aspects that have been rarely considered thus far. Let's start with the introduction. Trust and reputation have been extensively studied in various disciplines and applications over the past decade. Metrics and computation methods have been proposed for reputation based trust with a focus on e commerce platforms like eBay's rating system for sellers and buyers. However, research in this field has also explored other contexts such as peer to peer networks, mobile and hawk networks, social networks, and ensuring data accuracy and quality in different environments. The computation methods range from simple arithmetic and statistical approaches to more complex graph-based models that consider factors like context information, propagation, and personal preferences. One issue is this in this field is that many new trust and reputation models tend to develop computation methods from scratch, overlooking existing proposals and resulting in underutilized models and approaches. This study, the author aims to promote the reuse of components and the development of reputation system by providing a framework based on reusable elements. They proposed a hierarchical taxonomy for the component of computation engines used in the reputation system, with a component repository containing pre-implemented components through web services. This paper follows the design science research paradigm and outlines the journal problem context research objectives. The author introduces a hierarchical taxonomy of computation engines components used in reputation system and explains the conceptual design and implementation of our component repository. Now let's discuss problem context and motivation. The widespread use of the internet has made trust and reputation system essential for decision making in network environments. In this work, the author has defined trust and its important properties and explained how computational trust models can establish trust. Specifically, they focused on reputation based trust and explored how research in reputation models can benefit from reuse. So, the first is the notion of trust and its properties. The concept of trust has been extensively researched for decades, but there is still no universally accepted definition. This is because trust is associated with various terms such as credibility, reliability, and confidence, and has cognitive, emotional, and behavioral dimensions. Sociologists view trust as a structural phenomenon, while psychologists see it as an interpersonal one. Economists interpret trust as a rational choice mechanism. In literature, the most commonly cited definition of trust and reputation in online context is reliability trust, proposed by Gambetta in 1988. This definition describes trust as a specific level of subjective probability that an agent assigned to another agent or group's ability to perform a particular action, regardless of whether or not the action is monitored and in a context that affects the agent's own actions. Next is reputation based trust. Trust can be established through different models, including policy based and reputation based trust. Policy based trust involves exchanging hard evidence such as credentials and is considered as hard security mechanism. On the other hand, reputation based trust is based on the history of interactions and is viewed as a soft security measure. Our focus in this work is on reputation based trust, which is determined by what is generally believed or said about a person or entity's character or standing. Next is research gap, the design of reputation system with reuse. There is a lack of research on the design of reputation system with reuse. While most trust models proposed in the academic community are built from scratch. Very few authors continue to develop ideas from previous works. This results in many potential models and ideas being overlooked. Reuse is a well known concept in software engineering, but there are only a few works proposing components that can enhance existing approaches. The author aimed to close this research gap by providing a framework for designing reputation system with reuse, and the approach involves creating a hierarchical component taxonomy of computation engines used in the reputation system and setting up a repository of design knowledge on both the conceptual and at the implementation level. This repository can be used by developers to select, understand, and apply existing concepts, as well as encourage researchers to provide new components. The goal is to promote the reuse of ideas, concepts, and implemented components and facilitate the components of reuse knowledge. Now let's discuss a hierarchical component taxonomy for computational methods in reputation systems. This research aims to create a taxonomy for existing models, and it involves two steps. Firstly, we'll analyze the journal process of reputation systems. Secondly, we identify the logical components of the computation methods used in popular trust and reputation models. So, the generic process of reputation systems. The process of reputation system can be simplified into three steps: collection and preparation, computation, and storage and communication. During the collection and preparation phase, the reputation system gathers information about the trustee's past behaviors and readies its future computing. Personal experience is the most dependable source, but it may not always be available. Thus, the data from other resources must be gathered. Next is the computation phase, which is the central part of every reputation system and takes the reputation information collected as input and generates a trust value as output. This part of every system and reputation system is feedback aggregation, which is divided into filtering, weighting, and aggregation. The context setting involves a truster who wants to establish a trust relationship with the trustee by providing context and personalization parameters and receiving the trustee's reputation value. Once the reputation scores are calculated, they must be stored locally, publicly, or both, depending on the reputation system's structure: centralized, decentralized, or hybrid. Reputation systems typically provide not only the score but also additional information to help users understand its meaning. Additionally, to ensure the transparency, the computation process should be disclosed. This paper focuses on the computation phase, which is independent of the system structure and can be applied to both centralized and decentralized environments. As a result, this approach is useful for designing systems that can be reused. The collection and preparation phase and the storage and communication phase are highly influenced by the reputation system structure and are not focus of this paper. Next is hierarchical component taxonomy. This section provides a detailed examination of the computation process. The author presents a new hierarchical component taxonomy that is based on the functional blocks of reputation systems commonly identified in this study. Beginning with the filtering phase, the three broad classes: attribute-based, statistic-based, and clustering-based filtering can be identified. The referrals are weighted in the second process step based on the different factors. Context compatibility. Reputation data is always bound to the specific context in which it is created. Next is criteria compatibility. Besides the context in which feedback is created, the criteria that underline the evaluation is important. Next is credibility or propagation. In network structure, such as in the web of trust, trust can be established along a recommendation or trust chain. Next is reliability. Reliability or honesty of referrals can strongly affect the weight of reviews. And then is rating value. Trust is event sensitive. For stronger punishment of bad behavior, the weight of positive ratings compared to negative ratings can be calculated asymmetrically. Next is time. Due to dynamic nature of trust, it has been widely recognized that time is one of the important factors for weighting of the referrals. Last is the personal preferences. As discussed above, reputation systems are used by various end users like human decision makers or services. Therefore, our reputation system must allow the adaptation of its techniques to subjective personal preferences. Next is the third step of the computation process, that is the aggregation. In this process, one or several trust or the reputation values are calculated by composing the available information. The list of proposed algorithms to aggregate trust and reputation values has become very long during the last decade. The most common aggregation techniques and classify them into four blocks, that is simple arithmetic, statistic, fuzzy, and graph-based models. Now my group member Nikit will take over. Thank you.
Niket here, so I'll move further. So I'll start with the component taxonomy as a framework for design with reuse. So in this paper, as Kamalpreet previously mentioned, the hierarchical component taxonomy. So it serves as a natural framework for the design of reputation systems that can be reused. And to support this process, we set up a component repository combining knowledge and a service repository. Thus, it does not apply not only contain information about software components on implementation level, but also provides extensive descriptions of the ideas applied on a conceptual level. So, this is the conceptual design of the component repository, and there's a figure which says the logical layers of component repository for design with reuse. These are some things that Kamalpreet mentioned earlier. So, the reuse-based software engineering can be implemented on different levels of abstraction, ranging from reuse of ideas to the reuse of already implemented software components from a very specific application area. So, therefore, the developed repository provides this knowledge for reuse on two logical layers, as it can be seen on figure. So, I'll move further with the conceptual layer and its reuse. So when reusing the implemented component, one is to unavoidably constrain the design decisions that have been made by the developer. And a way to prevent this is to conceive more abstract design that does not specify the implementation. Design patterns are descriptions of commonly occurring problems and generic solutions to the problem that can be used in different settings. Next, the reuse on a implementation level. So on implementation level, we provide fully implemented reusable components by means of web services in a service-oriented architecture. These services encapsulate the concepts of logic and functionality in independent and interchangeable modules to achieve the separation of concerns. All services provided here are registered as artifact in the services repository. So I'll tell you what is an artifact. So an artifact contains essential information about one live reachable service, such as service ID, its type, base URL, descriptions, parameter, example calls, design patterns, and implemented by the service and tag describing the functionality. Next, the implementation of the repository. To demonstrate the feasibility of our approach, we have prototypically implemented repository as a web-based application in a three-tier client-server architecture. So this is the figure of this whole architecture. On the server side, the logic is implemented in PHP on an Apache server. That's a logic layer connecting to a MySQL database persistent layer. The MySQL database contains all data regarding a design pattern as described in table. Each of this design is also implemented in a web service to enable a standardization realization of new web services and a flawless call via standardized interface. We employ an abstract class component. All of the components implemented as web services must have to inherit from this class, which particularly requires that we have to override the function values of the calculate underscore values. To make the generic component independent of input data, developers are advised to make use of PHP function func underscore get underscore args. In this way, distinct components of a can receive a variety of arguments. To consistently handle the client calls, our architecture is extended by a web service call helper. Now, side. The client side, that is a usually presentation layer. We employ current web standards consisting of HTML5, JavaScript, CSS, and a bit of a bootstrap. The front end is divided into three main pages: overview, knowledge repository, and a service repository. which provide information on the general concepts, the trust patterns, and the web services. To enable a standardized call of a web service from a client side, a web service call helper allows a simple call of each component by configuration and provides all functions necessary to establish a connection to the repository. The configuration details are passed to one constructor, which requires base URL and output format. It can be either XML or HTML or JSON and a unique component name. The uh, this is the example of a service call helper constructor and the arguments that we pass to it. So here is the base URL, format in HTML, and specific component name, and then we call that function. Now we'll move further with evaluation. To rigorously demonstrate the proper functioning and quality of our approach, we carry out two-part evaluation of our artifact in this section. As there is currently no comparable framework, we firstly perform a descriptive scenario-based evaluation followed by a static analysis. So first is the scenario-based evaluation on the reputation systems development. So we'll consider a scenario here. So there's a fictitious web developer called John. John runs an electronic marketplace platform for pneumatics and philalists. The platforms have been launched with his friends as the first users, and since it is growing so fast, most of the users don't know each person in anymore. And as a result, many of the initial users have stopped interacting with the newcomers as they do not trust them. This is completely understandable. And after realizing this problem, John decides to introduce an online reputation systems in order to establish trust among strangers. So these are the some of the component sequence for the John's computation engine. And below is the code for the computation engine described above. So this scenario, what we get from this scenario is that our knowledge and service repository has an obvious utility from a practical point of view, since developer can get easily access and gain knowledge about online reputation systems. Thereby we may help to better spread innovative ideas and allow developers to experiment with different computation engines and techniques. The second analysis is static analysis that's done on the matching components and its trust properties. As our component taxonomy serves as a framework and design for new reputation systems with reuse, it should enable developers to extend current reputation model by ability to gradually include various properties of trust. Therefore, a way to evaluate the completeness of our solutions is to review whether a system that is built according to our framework could meet this standard. These are the properties that was being surveyed and analyzed by the researchers. So by examining the above table, we find that there are many proposals that have been developed uh, components to personalize reputation systems, thus covering the subjective property of trust. This reflects a general trend to enhance personalization of reputation systems. Furthermore, it becomes clear that all our weighting and aggregation components follow the fine-grained properties of trust. That is, trust can be modeled as a continuous variable. For the filtering components, the fine-grained property is not entirely applicable in the same meaning, as filtering has no direct influence on the trust value of referrals, since the effect on the filtering is that the referral either is further considered or not considered. It shows a binary character rather than being fine-grained. So in contrast to the subjective and fine-grained properties of trust, the properties such as context dependence, multifaceted, event sensitives are particularly addressed by only one or two components. So overall, we can say that the computation trust can be represented quite accurately when using our taxonomy and provided components as a basis for the development of new reputation system or the extension of existing models. Our approach requires specific knowledge on the structures of the repository, the functioning of each component, and details on how to plug the components together. Developers need to manually combine components and take care that they use valid input data and a feasible combination of reputation system components. In its current form, our framework is not very developer friendly. Therefore, further research is needed in order to improve the practical usability of our component repository. Our hierarchical taxonomy is currently limited to a functional view on the identified components, but developers may get benefit from the additional views. Because of the importance of the robustness of trust and reputation systems, we propose a taxonomy of attacks on reputation systems and then refer to the single components of our repositories as solutions to specific attack classes in a different paper. The next is this time and effort sensitive. As the selection and interpretation of adequate components of the new system requires a little bit of knowledge in this research area. Also, this uh, this this requires that at a particular application we have to devote more time and effort in order to fine grain these data sets and referrals. So to conclude, I would say we presented concepts to foster the use of existing approaches, and we provided a hierarchical taxonomy of computations components from a functional view, described the implementation of component repository that serves both as a knowledge base and a service repository. In this way, we communicate design knowledge for reuse, support the development of new replication systems, and encourage researchers to focus on the development of single components that can be integrated into various reputation systems easily to extend their capabilities by new features. Also, by matching the identified components and the properties of trust, we found that integrating existing ideas and concepts can lead to a reputation system that can widely reflect the computation trust by addressing all properties of trust described in this paper. The next is question answer time. These are some of the references that we have used to create this presentation. That's it from our side. Thank you so much for your time.